Hey guys, hope you're all doing good and welcome to a new video. So today we are going to be discussing the results that we obtained from the pressure relief valve. Alright, so the first plot that we are going to be looking at is the position of the spindle as a function of time. So here a couple of interesting features can be noted. So the first feature that I want you to notice is the alternating nature of the position curve. So you can see that the spindle is moving up and down, and if you look at the amplitude of this variation, it's increasing over time. So the reason why it's first alternating in the first place is because that is how a pressure relief valve is supposed to work. So the spindle goes up to a position where it can relieve enough fluid pressure so that the pressure in your main line is actually reduced to a point where the spring force actually dominates and pushes back the spindle, right? Not just the spring force but also the mass of the spindle. So this process keeps on occurring. Now the reason why the amplitude of this curve or amplitude of this wave, right, increases over time is because of the increased inlet pressure, right? So as the pressure in the inlet line keeps on increasing, the maximum displacement of the spindle is going to increase. And at some point, what we have done in our inlet pressure profile is that we have ramped the pressure down to baseline pressure, right? So the pressure is reduced, and that is why after some time there is this sudden drop in displacement and the valve shuts closed again. Now if you look at the velocity of the spindle, that can be presented here as well. You might be wondering what is it that we plan on achieving from this particular data. So you can actually learn a lot. So here you can see that for this particular made up operating conditions, we are running the simulation for about 1 second, right? And for that 1 second you can see that there is a particular frequency, and I will leave it up to you guys to figure out what that frequency is. So this frequency helps us identify the cyclic load on the valve. Now this cyclic load information can be used to run a fatigue analysis using a structural solver on this particular spindle, and that can be used to predict the life of this particular proportional valve. Now in this particular case there are a lot of things that we have not modeled accurately, so we will be discussing that. But in general, if all those modeling assumptions have been ruled out and if the simulation is set up very similar to a real valve, then this is the data that engineers would be requiring. Now in addition to this, you will also be looking at pressure load on the spindle, right? So you can just create an animation where you can color the spindle by pressure using Insight or ParaView, and you can take that pressure map and feed that into an FEA solver for basic strength calculations. The force diagram is actually interesting because you can see that the force is kind of fluctuating around zero, and this might be confusing to a lot of people, right? But you need to understand that the initial level of forces is around 7,000 newtons. There is negative sign because of the direction in which the force is acting. Now remember, this is the initial force that's keeping the pressure valve closed, or at least keeping it at the lowest position, right? Now from this lowest position, what we are doing is we are running the simulation, and the fluid is almost imparting 7,000 plus newtons of force, and that is why the spindle is actually opening in the first place, correct? And it's kind of keeping it in that same zone, right? And that is why you see that your displacement profile also fluctuates, right? That's because of the force that's acting on the pressure relief valve. Now in this particular case, again, as I said before in the previous slide, we are not making some assumptions correctly, and I'll kind of go back to Converge Studio to explain what those are. If you do that, we're able to fix the errors in the assumptions that we have made. This plot would look much more realistic. And here you can see that after the inlet pressure line restores to its original value, the force again goes back to its baseline values. So this kind of tells us that the simulation is behaving properly. So now let's take a look at a simple velocity animation. For your assignment, you will be doing a whole range of post-processing. So I'm going to be showing you only the velocity animation to kind of show you how the results look like. Now you can see how the valve just goes up and down. It's just like a pressure cooker if you have one. And you can see that once the inlet pressure drops, the flow field eventually dies out. So let me just play this again. You can see that initially there is a lot of movement in the valve, but as the inlet pressure is slowly dropping, you can basically see that all the action dies down. Now the important assumption that I was talking about, I'll just show it to you, and I'll kind of pause the video in the right location. at this point, if I just move up, you can see that the inlet pressure is restored to its baseline value, but you can see that the flow is still taking place. In other words, this particular computational model lacks a very, very important concept, which is pressure buildup. Now, so for those of you who have seen pressure cookers, you know that the pressure actually builds, and once the built up pressure is higher than the pressure it takes to lift the valve, you will basically have pressure relief, right? But in this particular case, we don't have a completely closed seal between the pressure line and the rest of the pressure valve, and this is a fundamental flaw in our computational model. So then the obvious question is, how are we going to fix it? Well, the short answer is, you can set up something called as events within Converge Studio, and that way you can treat the pressure inlet and the rest of the pressure valve as separate regions, and you can control when those regions would be connected and when those regions would not be connected. The actual problem comes from the fact that two surfaces cannot intersect in pretty much any type of simulation tool, right? By default, it cannot unless you have some type of contact model in place. Now, in this particular version of Converge, we don't have any contact modeling, and hence we cannot have the pressure buildup. However, you can write a user-defined function which would basically disconnect these two regions. When I say disconnect, what I simply mean is flow from this particular region cannot go inside this particular region, because currently you can see that there is a jet of fluid flowing here, right? You can stop that from happening. If you stop that from happening, you will have the pressure buildup process, and you know what? Your valve opening profile would look much more realistic. Alright, but in this particular video, I'm not going to be showing you how to write that user-defined function. Alright, with that, I would like to conclude this video. Now, as part of your assignment, what you will be doing is you will be running the same simulation with adaptive mesh refinement. That is one thing that you will do. And in addition to that, you will also be looking at the maximum pressure force acting on the spindle, right? And you will also obtain a pressure map or a pressure field map on the spindle. Okay, so with that, I would like to conclude this video, and I'll see you in the next one. Bye.